Hello and welcome to the Extended Greg YouTube channel. I'm Greg and today we're going to be building a weather station. It's going to be great for knowing exactly what's happening outside as you get up for the day. But before we get into it, be sure to hit that like button and, hit that subscribe button if you haven't subscribed. But let's get right into it. It's going to be an exciting time. Okay, so what we have here is we have the RP, so this is the Waveshare RP-2350, and it's the new version of the Raspberry Pi Pico, in effect. It's that same microcontroller. The other one for the Pi Pico 1 was the 2040. This is the Pi Pico 2, which is slightly better clock rate, a little bit more resources in terms of RAM and in terms of storage space, but completely interoperable. So at the end of the day, I'm using this because it has the hardwired interface. And I wanted that because I want to be able to shield it a little bit against things like, close lightning strikes, things like that. Since it's going to be outside, I don't want it to be fried, right off the bat. I want it to last for years and years and years. So this is pretty much USB-C in, which is also an advantage versus the Raspberry Pi Pico 2, which has micro USB. But it is something where it's got slightly less I/O, but plenty of horsepower. And the way that this is actually implemented is that it doesn't treat it like Wi-Fi. It actually is a separate little microcontroller that actually lives under the Ethernet port. So it's, in effect, giving you an extra processing core. And we're going to take full advantage of that with the code. I'm going to go through it. We're using Thony. We're not actually going to commit any of the code. I've already run it, so it is already running. So we're not going to do any debugging or anything else like that. And I've also posted all of this code on GitHub. But this is my working example here. We have actual Ethernet connectivity. I have an SHT31 humidity and temperature sensor currently attached. And then the rest of the stuff is pretty much just contact closures. So I don't have that shown here, but I will show you some examples in a second. But it is all going to be powered through PoE. Now, I did try finding one that's fully integrated, and technically there is a feather wing that does PoE for the RP2040, which is the previous version from Adafruit, but I didn't see it for the 2350 available to where I could get it easily. So I went with the Waveshare instead. Otherwise, it would have cut this down. Also, if I did actually go with like a solution like an ESP32, I'll show you this really quick. So this is an ESP32 variation of the same thing. So it's got the Ethernet port on it. It's got USB-C. It's also made by Waveshare. But this is the full Pico layout. It also has an SD card slot. And then it has camera port, things like that. But it has this nice little header here where you can actually plug in directly to it a little PoE hat that just sits right on top. Now, ideally, they're going to come out with something like this, and this is the PoE hat. So, all right, it's got all the necessary connections, everything else, but then it sits within this form factor and is able to just take it right out of the box, just straight PoE, and be able to power both this and, whatever accessories you would have. So, in this particular case, I didn't want to go with ESP32. I did want to go with the Pi Pico. Just since they came out with a new chip, I just wanted to try it out and come up with a good test project for it. Plus, right now, I have a number of I'm using Arduino and a Raspberry Pi, so I thought it was fitting to kind of go with the Pi Pico just for my own sake. So this is a project I'm actually going to implement personally. So just kind of jumping into it. So I got a Visio here, just with some actual shapes or the some of the devices drawn in here. So we have the RP2350-ETH. Okay, I just showed you that. I also showed you the SHT31. We can kind of zoom in here and let me hover over. and you can kind of get a better look at it exactly what it is. So it's just I2C interface. It will give both the humidity and temperature readings simultaneously, and it's all detected through this one little chip right here. And it is mountable, which is nice. In order to detect the wind speed, I have an anemometer, but they're available off the shelf if you did want to replicate this project for yourself. So an anemometer is just the cups, and it spins in the wind, and it tells you how fast the wind is actually going. And what these actually use for their sensor mechanism is usually a Hall effect sensor. So they'll have a Hall effect sensor that every time that it completes one revolution, it will close that contact. And we're going to use interrupts in order to read that, and that will, the number of counts over a certain period of time, over a second, is going to tell us how fast the wind is moving. You can also actually time the distance between the two pulses in order to get an instantaneous reading, since technically you're averaging if you're going across a second, but in this particular case it will do both. Then we have a rain gauge. So this will actually collect an amount of water that is of known area, and what that will do is it will drip down into a cup that is scaled for the size of the catch basin. And every time that it gets to, like, usually around 0.01 of an inch, or, you know, X number of millimeters of rain, it will tip and trigger a contact closure. And that's actually how it comes up with the with the rate. So again, based on the distance between those two pulses, or number of pulses over time. Usually they're very slow, so I would say the distance between the pulses, that will give you your rain rate. And then scrolling up here, to close out the wind, we have the weather vane. And all this is a potentiometer, and it's just a continuously rotating potentiometer, but it's 3 wires, so it measures, you would hook it up to an analog input, and based on which direction it's turning, usually I like to align north to be, the 0 point, maximum and minimum voltage. But, it's really whatever you want it to be. And in this case, that is how it's set. But you calibrate it based on the direction that it's pointing, and based on that, it will tell you whether it's going north, northwest, northeast, etc., south. Whichever direction it happens to be pointing based on where the wind is blowing. So that's kind of how we're getting everything into this particular thing here. We're hooking it all up to different pins. It's all basic contact closures with the exception of the output, the sweeper for the weather vane, which is analog, and the I2C connections here. Everything else is basic contact closures. So going over into Thony really quick. This is actually a pretty complex program. I used Google Gemini version 2, and I wanted to try out its programming capability. I did start with a script that I wrote previously for Arduino in order to do all of the conversions and everything else like that, but I ran into a couple of challenges where I couldn't necessarily do everything that I wanted, or I had to come up with new ways in order to be able to implement it. So, for example, with the NTP, because obviously if it's going to create a certain time-stamped capture of sensors, it's going to need to know exactly what time it is. With the particular Ethernet connection, it makes it difficult because of that separate processor. So the actual communication between that and the RP2350 is serial, and it uses some very specific commands, but you don't have the direct access to it like you do the Wi-Fi on the Pi Pico or the Pi Pico 2W. So it is something where there's a bit of a trade-off there, and specifically what it's using is the CH9120 controller, and that's the actual thing here. So we wrote a little library based on the datasheet in order to get that to actually connect, and also based on some other examples. But it will set either a static IP address or set DHCP in order to be able to get that all set up. You can choose your ports, and you can choose your destinations, things like that during runtime. So pretty much it's going to call and set up that config based on what you have in a config file. So this config file lives separately, so that way you don't have to go into your code and start modifying things. I do have this posted on GitHub. The link is in the description if you want to check that out. I would say it is a work in progress, so take that with a grain of salt. It may be a little bit messy, but I did try and clean it up before the video today, or before the stream today. So as far as the, you can set DHCP. You can set static IPs. Obviously, if you set DHCP, it's going to ignore all of these. But then you're going to set your MQTT server IP as well, which is going to be your destination. So the AH9120 is able to connect pretty much to one destination. It doesn't treat it like a regular... it's not like a regular network connection. It abstracts it, so it's like an open socket connection. So you're just communicating with another machine directly. You're not communicating with the whole internet. So it's a little bit different. It does work for MQTT just fine. I did run into a number of bugs trying to get it to work initially, which was a bit of a fight, but it is working consistently. I have had it running for the past week or so. It has been consistently delivering those statistics. So once it's all set up and connected to the network and connected to the MQTT server, I brought up the thing about the NTP earlier, and it's going to automatically subscribe to a topic, which is NTP/time. And there's some accompanying code here I have to finish up, which is, in this particular case, I created a very simple Docker. And all that Docker does is it publishes the current time to the MQTT publish point NTP/time. So that's where it originates. So it's getting it from a server that is running this Docker, and it's just using a traditional library. So it was like 5 or 10 lines long. It's not very long at all, but that's how it's able to synchronize it. And potentially in the future, I may actually start using that for more related types of projects where it's using this particular microcontroller, since you can have multiple clients receiving that particular time frame, and it'll be well within a second, which I think is perfectly appropriate. I'm not doing scientific measurements here. I'm just trying to come up with general things, and it's not going to determine offsets or things like that based on that time. It's only going to be what it timestamps its particular its published messages for the current sensor status. So it won't impact or have any impact at all on, for example, the rain rate or wind speed. So as far as the going on from there, so it actually, I have the MQTT client broken out here as well, and this is something where it's all very low level, because again, it's not aware, it's just treating it as a socket connection. So you can actually go and see the hex values and things like that that are being published within the message in order to create the actual, or send or receive or subscribe, for example, to, which you should do to this video, to this channel, but to the particular messages that you want to receive. And so it's actually quite a bit. So it's only about 325 lines long, which I think is pretty compact considering what it's actually trying to do and how big some of the other libraries are. So outside of that, the only other library that we had to create was also from the datasheet was for the SHT31. And that's the temperature sensor, which I'll just point to it on the screen. Right, so that's this temperature sensor right here. Wonderful circle. Oh, that's much better. So it's that temperature sensor, and pretty much those are available for about a couple dollars from Amazon. All of this is not very expensive. It can be very expensive, but if you shop around, you can find stuff that's, I would say, consumer grade. The issue I always had with trying to get something that was pre-built was that it really was a circumstance where they would always make it a closed system. So you'd have to reverse engineer their protocol in order to be able to actually get any reasonable data out of it in order to ingest it into, put it into something like Node-RED or N8N to be able to aggregate it and do some reasonable work that wasn't a part of their existing ecosystem for whatever vendor you were getting it from. So that's part of the reason why I choose to build it myself, and that allows me to integrate it into other Python environments, things like that. So like, for example, the clock that we built on this channel before, the NTP clock, at my house I have it showing the current temperature, exterior temperature, so I can see it as I'm getting up, as well as wind speed, things like that. So it just makes it a lot easier to integrate in that way. And I'll show you this as well. So this is actually a Lacrosse. I think Accurite makes one as well, but it's actually for one of their stand-up sensors. But this is what I'm going to put the humidity sensor in, right? Because it needs open access to the air in order to be able, and no hotspot, so it can't be disrupting its own thing. So you can't put it inside of a sealed box. Otherwise, you're definitely not going to get any humidity readings, and you'll probably get the wrong temperature reading because of the heat that it generates. So what this is it's pretty much a series of overlapped cones, but it is actually open, so as wind goes through it or heat rises up through it, it's just going to evacuate out of there and create a convection, but you'll get an accurate time and temperature and humidity. But if rain falls on it, it's sealed enough to where it actually won't be able to reach the interior because they're all overlapping cones. So I would mount it to this, put a cable coming out of the bottom, mount this somewhere near the other sensors, and plug it into the box. So what box am I going to put this all in? That's another good question. So I have one of these boxes, and what this is it's just a outdoor weather enclosure. And I do want to point this out. It is metal, because I want to shield all of this in order to be able to make it so it's not going to be disrupted by EMI or things like that. I mean, there's a lot of electronic connections and especially analog connections that we're trying to take sensor readings off of. So at the end of the day, it's not something I want to be leaving to chance or putting it in a plastic enclosure, although you could. So just something to keep in mind. I just choose metal. The one I had previously was just a standard square box where the door was exposed on the top and I didn't have a cover over it. So all the other ones that I have like that, that are under like eaves near the house, things like that, they're all fine. But for some reason, this particular one started developing a leak, which is part of the reason why I'm going through this. So it has a Raspberry Pi in there right now. The water drips past it, but it's not necessarily something I wanted to repeat with this, even though it's just, a relatively less expensive little thing, and the box I got is kind of overkill. So there's more going to be going in there. We'll go over that in a second. But pretty much what this is it just has a nice little latch. It does lock, although the lock is a joke. You can open it with a Dream and a wisp of air. But it's got a nice little rubber gasket that seals against this, which is, it's a little flange that goes around the outside. And then it's got this nice little galvanized plate on the back that you can remove to be able to mount everything to it, which would also be a good ground plane for everything. And the door, everything is shielded. So they're bonded together. I haven't tightened anything here because nothing's installed. And then this will mount somewhere in order to be able to, that'll be where it lives. And the way that the top is designed, the water should hopefully roll over the front instead of coming into the back and potentially leaking in somehow. But there's tons of enclosures available. I mean, they make them literally in all shapes and sizes. So one thing, since we're talking about shielding and things like that, there's a couple of things that I wanted to do in order to try and harden this. And one of the main things that I want to do is include a lightning arrestor for the Ethernet connection that is PoE capable. This was pretty much the cheapest one I could find that was in an enclosure style that I liked. They make bigger ones, and they make them with gas expansion tubes, things like that. This happens to be a gas expansion tube one, and that way I can bond it to the case. It's kind of weird because I'm using shielded Ethernet, and that's going to be the ground, and I can't really put in a ground rod for direct lightning protection, but I just want to carry away stray transients that could disrupt readings or destroy the equipment. So this should at least keep that from going crazy. There are also isolated PoE extractors, things like that, to where it'll take a couple thousand volts of transients and completely ignore them. So that's something to keep in mind. But that would go upstream of the PoE extractor. So it would be before here, and then this would connect into the PoE. The PoE, the network, would go into the RP2350. And then I have the power output. This one happened to automatically come with the USB-C. So I have it going and powering this particular device. So, and it's way more power than it needs. And it actually is possible that that could be an issue, because sometimes they don't measure for minimums. They only measure for maximums, but this will do full gigabit, things like that, and the operating temperatures itself are fully fine, and I could upgrade this in the future and be able to keep this in operation. So that's pretty much how that goes. So that's going to protect the Ethernet side of that. But in order to protect the other signals, because I'm going to have signals coming and going, I'm going to have a connector and things like that, I want to set up some isolation where possible. So the way I'm doing that, and actually I'll try and keep this decluttered. The way I'm doing that is I'm going to use an opto-isolation board. And I could have just built this, but I decided to just go with a pre-built one. And part of the reason for that is that it just has everything already set. So it's got resistor packs here that already set all of the values, everything else. It's on a nice little circuit board. I can choose to keep or remove the terminal blocks here and potentially directly solder to it. And it will mount very nicely to that steel plate. So that way I could just replace it if I ever needed to. But it has enough inputs to be able to buffer all of the signal lines, and it will do actual opto-isolation for all of the digital inputs, which are the wind speed, the rain sensor, and potentially some of the other stuff as well. I'm not actually going to do this for the I2C temperature and humidity, the SHT31, but so it's got way more capacity than I need, but that's totally fine with me. So that will take care of those particular sensors, but for the other stuff, like the analog inputs, things like that, what I have here are two types of what they are TVS, or transient voltage suppressors, which are effectively Zener diodes. So what they'll do is they will act as, they'll be at high resistance, like extremely high resistance, whenever they're in a situation where it's within their normal working voltage. But once it exceeds that voltage, then it will act like a short. So you would usually set this up so it would be going from your signal wire or from your from your power bus to ground. So that way, if it exceeds a certain voltage limit, it will then ground it out and cap it, so it'll create that max voltage. So that's over voltage protection in effect. So when you see that on power supplies, things like that, that means they include one of these. So I have two of them here. I have one of them for 3.6 volts, since this is since the RP is a 3.3 volt device. So 3.6 volts is well within the operating range for any of those inputs, so I can cap any of those inputs at that voltage in order to make sure that it's staying within the range and it's not going to blow it up. So if it does have a fault condition, hopefully it would be something that would, if it's from the environment especially, would be lasting only a few milliseconds and then would correct itself. And that can happen from things like having a nearby lightning strike can induce the electromagnetic interference, or pretty much a voltage on any longer conductors that you have, especially ones that are not shielded, and induce the voltage on them and potentially burn out electronics. So that's why a lot of stuff inside of computers, things like that, is shielded, is just to reduce the chances of that kind of stuff happening. Or if you're near an AM radio station, for example, it will definitely induce a voltage on it. So this would work to be able to cap that voltage to make sure it doesn't exceed the operating parameters of that particular input. And then for the power rail, I also have this, which is 5 volts, so I can put it on like the device end. So for things that do need 5 volts, etc., I can put this on, cap it, and actually do protection at both ends. So opposed to just doing it at the RP2350 end, at the microcontroller end, I could do it at the sensor end as well, at the other end of that cable. And as long as I have a separate ground path that's not part of that is actually connected to ground somewhere, I can create that lower resistance path back to Earth to be able to protect the circuits and protect the active electronics on the other side, or protect the potentiometer or the Hall effect sensor, things like that. So that's the kind of stuff I'm doing in terms of getting that all up and running. I don't have it fully built as of yet. I'll put some pictures in the GitHub when I do actually get it all built, or do a follow-up video if there's something that needs to be changed or I've learned from it. But just going through the actual code itself in the main script, that's what defines all of our pins here. So if we needed to know where to connect everything, so we have our rain sensor, which we could actually do this as a side-by-side and just connect them up as we go. That is way too small. There we go. So, and I'm not going to include any of the other stuff that I have as far as the transient voltage suppressors or anything else like that. I think it's just going to make it a little too convoluted. So we have our rain gauge is going to go to pin 2. And I did put some nodes on here just to make it so it snapped to it a little bit. And I think that'll do. Right, so we have our rain sensor on pin 2. I'll zoom out a little bit. We'll do our wind sensor. So we have our wind sensor, which is our actual speed, and then our wind vane. So our wind sensor, which is the anemometer, goes into pin 3. And then we have our wind vane, which will go into pin 26, which is one of the analog inputs. That's why it's not in order. Then we have our I2C pins. So we're going to use pin 5 for SCL and pin 4 for SDA, and try and keep this from becoming a rat's nest. So let's move this up here. I feel like it didn't go. Just for the record, if you are using Visio, the way to add a node to it... Oh, I see it. Is you just control click. So if you do control with the X option selected, that's how you add a node. Just make sure you click it first. I like it just because you can add the actual pictures, everything else like that, but there are better tools out there, especially ones that are open source, to be able to do this exact same thing. So choose with the tool that works best for you. I'm just trying to do this quickly, as it were. And we'll just make this a little bit nicer. Right, so 5 is SDA, 4 is SCL, And then we have the SHT address is 0x44. That is by default on here. If you did actually short out another pin, some of them do have address selections where you can choose an alternate address, but it's usually just one of two. So the default is fine in this particular case. As long as we don't have multiple, the addresses won't conflict and that won't be an issue. And then as what it's actually going to publish to when it does capture all of these readings is weather. And actually, let me make this full screen just so you could see this really quick. So that's pretty much the connection right here. There is some power that goes here. So for example, we want this to go between 0 and 3.3 volts. And ground. We'll choose a ground pin where it doesn't overlap. Okay, so we have our ground connections, our power, and ignore the fact that the arrow is going backwards. Same deal with here. We would have a pull-up resistor defined within the software when we actually set it up, but this would also connect to ground as well for another connection. Right, so we have a ground and we have our signal going out. So pretty much it's going to short it to ground as it's going. For the anemometer, we're going to do the same thing. And some of them will be more than one wire, so will require power. If it is Hall effects, if it's a reed switch where it's magnetic, then usually it's just a ground connection and you use an external pull-up to be able to do that. Let me just try and make this a little bit less meh. Close enough. I could have reversed these. I mean, literally, they're completely arbitrary. Look at that. That looks much better. Okay. So I wish I could say that this was a beautiful drawing. If I added colors, things like that, I think it would look a lot better. But that's kind of the overall gist of actually what's being connected. Mine's going to be unnecessarily more complicated, but it is just something where you make it as complicated as you want. It's your project. You know, it's something where you can enjoy it. I do have the source code, which will work with whether you add any of the protection circuits or not, since those are all transparent to it. But that kind of gives you the overall view of what the physical implementation is. On the code side, everything else beyond that is all set through the config setup, which is just the IP address and the MQTT server name and port. And for this, I just happen to use a default installation of a Docker container containing MQTT. And that's actually what I'm publishing to. And it uses the same MQTT connection for both the NTP and the weather. And you can use it for other things as well. It doesn't particularly care. So at the end of the day, you kind of tune it to whatever you want. It is going to output in metric. Technically, in this particular case, some of the equipment that I have is doing measurement in inches. So it is actually going back through and converting that to metric for millimeters per hour, just so that way it's a bit more standardized, and then I can convert it back using effectively the inverse equation to be able to get it back into inches for since I use the US system. So, but it is using interrupts and things like that in order to actually take some of these readings. And the reason interrupts are a value to this, and that's one of the nice things about using the Pi Pico or the RP2350 or a Pi Pico, is that you pretty much can set an interrupt on any pin, and you can have multiple interrupts going at the same time. So we actually have a couple of interrupts going, so one for the rain tip and one for the rotation for the wind speed calculation. So for the wind vane, everything else like that, wind heading, it does the conversion all from there, but none of that is time sensitive. So it will disrupt whatever communication is going on, and that's part of the nice thing about actually offloading that network communication, is that it's not at risk of fouling any of it. So but it's kept as short as humanly possible, but it's just doing counts, things like that. So for the rotation, it's just going to add 1, and then it's going to see how long after a second has elapsed, how many ticks have happened, and that's your wind speed. And then for the rain tip, that's where we do it based on ticks and milliseconds, things like that. And this may need some debugging, just because when it does eventually roll over after it's been running for a while, that may cause a false reading every time that happens, which I think would be every couple of days or so. So still a little bit potentially to debug there, but for the majority of it, I would say it should be good. But that's something that, you know, part of the finesse of it, but it will work out of the box. And let's see, so some display. So it will actually show some things. I can hook this up to Serial really quick, so we can look at a couple of readings as they're coming out. It is actually publishing to the network port right now onto MQTT, but I don't have a reader that I can use to demonstrate to be able to show you. So I'm going to unplug this really quick. I should show you what I'm doing. Right, so I'm just going to plug in a connection to the computer. Right. Just hit stop. And then I'm going to hit run, which is one of these. And I can't see which one's which. Oh, it's going to do that, isn't it? I might need to just run it from here. So I'm just going to run it by just hitting the play button. We will drag this up. It's still got a bunch of debugging in there. So you can see all of the commands that it's actually sending in order to initialize the network, everything else like that. And right now it's not able to connect to the MQTT. So it's going to reinitialize again. I did try and add as many while loops as possible to make it self-recovering. So if you disconnect the Ethernet port, for example, and then reconnect it, that you're not going to be in a circumstance where it is sitting there doing nothing forever. But still some potential bugs and things like that based on how it actually connects to it. So if this is the case where it just keeps rebooting forever, I'm just going to disconnect it. Reconnected. I could have done that through software. Hit stop, hit play, and let's see. It should be able to connect. And let me actually make sure. I'll see if I could pull up the MQTT server really quick. And get you a log so you can see what's going on. Because I do have some pretty verbose logging. Let's see. So I'm running this on an Unraid server as my actual host for my Docker. Oh, connected. So there you go. So right here you see it's, right now we don't have any other sensors connected to it. So you can see that the humidity, Celsius, everything else like that. And then it shows the encoded publish message as hex for what it actually sends. And then it shows you that the message was sent. So it is sending it as JSON in the actual MQTT message itself. And it's just in the middle, it's going to be constantly pinging for heartbeat purposes. So that way you know it is actually connected. And I'll just pull this up just so we could see it on the other end. So I gotta see what the where it is. So this is the default install. I turned on verbose debugging log messages in order to make that something that was usable. And we'll just tail it. So we're seeing all of those ping requests come in. As it was trying to connect to things like that, we could have seen those connect messages as well. But we see received published message right here, 245 bytes, etc. So we see those coming in about every 4 seconds. That is settable within the script, so you can adjust that as you wish if you only want to take readings every minute or you actually want to do it every second. So there it is running. And with the other side of this, with the every minute, it will receive the NTP message. So it is possible right now that the NTP is not accurate. So, you know, it does need handlers, things like that. So either I got to start reporting later or increase the actual NTP frequency. And that's just coming from actually a Docker locally on my machine. So it's this right here. And we see the time interval, everything else. So it's just showing the time, but this is actually the hex equivalent with some character interpretation showing when it's been published. And let's see if we can actually capture one of those, because it should be coming through. Let's see. I'm actually going to restart it just to make it reconnect. So we'll see the connection reestablish here for this particular client. Right, so we see a new connection here. We see it's coming in. The connection was acknowledged. Things like that. And now every minute we should see a packet come through with the actual timestamp. I kind of wish I made it shorter, but pull that off the screen just to give us a little space. But it's a very short packet for the NTP, so it's not very intensive for it to actually process. So let's see. It hasn't been running for a minute, so let's see. We're going to keep seeing until we see it. There it is. All right, so I'm going to stop this right here, just so we can scroll back to it. But we can see the time sync right here. So it is using UTC. That way it is generic, because I didn't want to have to do anything involving time zone offsets. So you can do that on the back end and have fun with that. But as far as the actual time sync message, and it's probably going to be something that I'm going to increase the frequency, but anytime it does see it, it will interpret it. And did a lot to actually manage the MQTT interaction, because this was one of the hardest things in terms of trying to get this to go. Was it kept it like you couldn't just, there's no delimiter or anything else like that. The way MQTT works is that it actually does it based on the count for number of bytes left in the message. So after a certain known fixed header, then it will tell you how many bytes are left, and you have to count. Your client is responsible for counting that, and then that's how it knows when the message ends. Because you could have messages back to back to back in your buffer, and you wouldn't actually know, so you would stream them all together. And that would either corrupt the data or make it to where, you know, you missed a message. And that was actually one of the issues I was having, is I was getting the acknowledge packet responses for the ping, but then it was missing the NTP because the NTP was getting kind of tabbed onto the back of it, and it was skipping it. So it is actually aware of how many packets, how many bytes in the particular packet that it receives, and it will count that and treat those as separate messages, at least within the scope of testing, to where if it receives a back-to-back ping response and the time response, it will interpret that appropriately. So it's something really cool, but I just wanted to share it and just show you exactly what I got in case you want to try it for yourself. So, and I saw quite a few people watching today, so I do appreciate that. I didn't see anybody type any questions or anything else like that, so I have been at least watching the best I can. But I definitely appreciate you guys hopping on here to watch. So thanks for watching the stream today. If you like it, be sure to hit that like button and leave a comment down below. And if you know anybody who would like this content, be sure to share it with them. I would appreciate it, and I hope they would appreciate it too. And if you haven't subscribed, please subscribe. It helps me out a lot with the YouTube algorithm and also makes me feel good about myself. But be sure to hit that like button, and that way you know the next time we're getting extended. So until then, take care.